In this video, we're going to talk about suggested homework problems from 9.10, Taylor and Maclaurin series. These are going to be series that exactly represent a function f of x. So let's talk first about how we know that the Taylor series for f of x converges to f. So this will be a definition. So it'll be an if and only if statement. The Taylor series for f of x converges to f of x if and only if, and we might abbreviate that IFF. It's math people. R of the nth polynomial is a function of x approaches 0 as n approaches infinity. So in the past, we've talked about series that have to pass the nth term test to converge, but if they did pass that test, it didn't tell you anything about convergence. It only just told you that if it didn't pass it, it would diverge. Well, in this case, we know that every Taylor series converges if it passes that nth term test. So if this remainder term, which is the nth term, way out there at infinity, goes to 0, we're good, and the series converges to our function f of x. So let's look at number 5. Number 5 is a pretty basic Taylor series. It's actually going to be a Maclaurin series since it's centered at 0. So f of x is equal to e to the 2x, c equals 0. So I'm just going to write f of x down again here because I'm making 2 columns for f of x and f of c, and then f prime of x and f prime of c, and then for f double prime of x and f double prime of c, and so on. So when I get down here to my nth derivative, I think you can see the progression that this was 2 to the 0, 2 to the first, 2 to the second, and the power of 2 matches my derivative. So this is going to be nth derivative of x will be 2 to the n, e to the 2x. And when I evaluate that nth derivative at 0, it will be 2 to the n. So my formula here for f of x is equal to summation as n equals 0 to infinity of the nth derivative at c, this formula we just found, times x minus c to the n over n factorial is equal to summation n equals 0 to infinity 2 to the n times x minus 0 to the n over n factorial is equal to n equals 0 to infinity 2x to the n over n factorial is my formula. For 11, f of x is equal to ln of x, c equals 1. So f of x is ln of x, f of 1 is 0, f prime of x is 1 over x, f prime of 1 is negative 1, f double prime of x is a positive 1 over x squared, double prime of 1 is going to be 1, f triple prime of x is a negative 2 over x cubed, f triple prime of 1 is equal to a -2. Fourth degree, or fourth derivative, excuse me, is a +6 over x to the fourth. Fourth derivative at 1 is 6. And I see the pattern here that the nth derivative of x is going to be, so starting here on this term, this is 0 factorial, this is 1 factorial, this is 2 factorial, this is 3 factorial, so it looks like n minus 1 factorial. It also looks like there's a sign changer, -1 to the 0. Let's see here. This was -1. This was positive. This was negative. So I messed up by not including a negative sign here. That flips all these signs. That looks better to me. Negative, and then, so that's positive, that's negative, that's positive, that's negative. Yes. So we're going with -1 to the, you can say n minus 1 or n plus 1. I usually use n plus 1. I'll make an adjustment later if I need to. And let's see, what else? Over x to the n, because the power of the denominator matches the order of the derivative. So nth derivative at 1 is a -1 to the n plus 1, n minus 1 factorial. So let's stick that into my formula. Now I'm not going to start at 0 because my pattern didn't start until the first term, and I'm just adding 0. So it would be 0, which didn't fit my pattern, out here to n equals 1 to infinity of -1 to the n plus 1, n minus 1 factorial. Don't forget your multiplier of x minus 1 to the n out here over n factorial. This is centered at c equals to 1, so that's why it's x minus 1 to the n. Now, n minus 1 factorial goes into n factorial n times, because this denominator would be n times n minus 1 factorial. So we're left with summation of n equals 1 to infinity of -1 to the n plus 1, x minus 1 to the n over n. That's a perfectly legitimate formula, but your book is going to shift it so that it has an index starting at 0 here. And so when I subtract 1 from my limits on my summation for n, that counter, I need to add 1 on the inside. So this would be -1 to the n plus 1 plus 1 is n plus 2, x minus 1 to the n plus 1 over n plus 1. And then the only other thing that I'll fix here is this is where n minus 1 would have helped me. If I had chosen that over n plus 1 and I shifted 1 to the right, it would just become an n. Like I told you, it would be the same thing if I had used n minus 1 as if I had used n plus 1, and I would fix it later. So imagine I made the other choice, and when I shift 1 to the right there, that's -1 to the n, because -1 to the n, or -1 to the n plus 1, or -1 to the n plus 2, whatever it is, alternates every other term. So it makes no difference if I shift by an even number here, that an exponent of n plus 2 is exactly the same thing as an exponent of n is exactly the same thing as an exponent of n minus 2, and so on. So we can always adjust these powers to be shifted by a even number, and that usually means that my sign changer will have an exponent of n minus 1, n or n plus 1, when I'm done. If it instead ends up to be something that is associated with 2n plus 1 or 2n minus 1, then those are always even or always odd. We'll deal with those if they show up, and they get rid of the sign changer altogether. But if the sign changer is going to stay in the problem, it almost always ends up with an exponent of n minus 1 and n or n plus 1. And write the simplest version of that you can. So this is the final answer that they want. You could solve for your interval of convergence here if you would like. This is a problem that would have a restricted interval of convergence, but I don't want you to worry too much about that. I will tell you that the interval of convergence for this problem is going to be open on the left-hand side 0, closed on the right-hand side 2. And you can verify that yourself if you would like to. All right, let's go ahead and look at number 29, which is going to use a version of this same formula. It's more closely related to this one up here, but it's centered at -1 instead of at +1. So we've shifted it a couple places to the left. So using the formula that's in the book for ln of x, this is our established series that they want you to memorize for ln of x. And I think you can probably see how it comes straight from the work that we just did. So using that answer we just got from number 11, we can go ahead and shift this, say ln of x plus 1. When we add 1 in here, it's a horizontal transformation of 1 to the left. So that makes this -1. And this side 1. And that's going to change nothing in here other than this value here, -1 to the n plus 1, and then substitute for x plus 1 minus 1 is going to be x to the n over n, and that's going to be my final answer. So I know that I started my series at 0 for my final answer on number 11, but if you go up a couple steps from that before I did all the shifting of the bounds, I had this work right here, and that's the version that the book wants you to memorize, and it has this restriction on there for the interval of convergence that we talked about last time. Don't forget to not only shift your series, but to shift your interval of convergence, because it was a horizontal transformation that affects x. All right. Next one is also very straightforward, using your table of Taylor series functions. So 43 says it wants the Taylor series for x sine of x. I should show you 43, not just write it down. There it is. I don't think I showed you 29. but 29 told us to use the table of power series for elementary functions, and that's why I did the problem that way. And then 43 does not tell us how to find the Maclaurin series, which is a Taylor series centered at 0. But it doesn't tell us that we can't use the table of functions. So let's go ahead and use that, leaving the x alone for right now. Sine x from our table is n equals 0 to infinity of -1 to the n plus 1 x to the 2n plus 1 over 2n plus 1 factorial. I want you to notice that sine is an odd function, so it has only the odd exponents represented here. We didn't talk about cosine of x yet, but it's only going to be an even function, and we'll only have the even powers of x represented. So this extra x, when it passes through the summation symbol, which it can because it's not n, it can pass through here, and x sine x is equal to summation n equals 0 to infinity of -1 to the n plus 1 x to the 2n plus 2 over 2n plus 1 factorial. And that's it for number 43. Let's look at number 67. I believe we'll wrap up with this. Yes, we will. I will need the calculator for this one. So get your calculator ready. 67 gives me some special instructions here, so I'll go back and read those. And it says that we want to use power series to approximate the value of the definite integral with an error less than 1/10,000th. And in our exercise 67, so one of the ones with some special instructions, assume that the integrand is defined as 1 when x equals 0. So they're telling us what the limit is there so that we don't have to do an improper integral and say, oh, this would be 0 over 0, and I would need to be getting close to 0 from the right here, and then they're just helping us out there by telling us that. But let's go ahead and use our definite integral here along with our power series. This power series is 1 over x times, and then we have summation of -1 to the n times x to the 2n plus 1 over 2n plus 1, n equals 0 to infinity dx. So now I have an x to the -1st here that's going to come inside. So this is going to be summation n equals 0 to infinity of -1 to the n x to the 2n over 2n plus 1 dx. I could pull all the things that are no, I'll leave all that alone. I just am going to integrate now. I can really swap these operators is what I was going to try and say, but I think you understand I'm using the power rule on every term here, that the integral of the sum is the sum of the integrals. So yeah, I'll swap the operators. You know you can do that, that's what my sum difference rule tells me to do. And then I can go ahead and pull these things through here that aren't bothering me because they don't have any X's on them. They stay inside the summation symbol, but they have nothing to do with this. So this is going to be summation n equals 0 to infinity, -1 to the n over 2n plus 1 times, and then this, according to the power rule, is x to the 2n plus 1 over 2n plus 1. So I'll pull that out there. This is evaluated from 0 to 1/2. This is summation n equals 0 to infinity of 2n plus 1, -1 to the n, x to the 2n plus 1, getting evaluated from 0 to 1/2 is summation n equals 0 to infinity, -1 to the n, this was squared, over 2n plus 1 squared times 1/2 to the 2n plus 1. If I put 0 in here, everything becomes 0, so I don't need to subtract a bunch of zeros. I can make this equal to summation n equals 0 to infinity of -1 to the n over 2 to the n plus 1 times 2n plus 1 quantity squared. So that's exactly what it equals in terms of a series solution. Now I want to approximate that answer to the nearest, to within a 10,000th. So I'm going to take this absolute value of this thing. So 1 over 2 to the n plus 1 times 2n plus 1 quantity squared needs to be less than 1/10,000th. When does that happen? Well, that happens when 2 to the n plus 1 times 2n plus 1 squared is greater than 10,000. Now, 2 to the n plus 1 is the same thing as 2 times 2 to the n, 2n plus 1 squared. This is not an absolutely necessary step, but this is 10,000, and I'm going to divide by 2 here to get rid of that 2 that's there, and 2 to the n times 2 to the n plus 1 to the second needs to be greater than 5,000. So this is where my calculator is going to help me. I could use a table, but it's hard to read a table. So I'm going to use the calculator to graph 2 to the x times 2 to the x plus 1 quantity squared. And I'm going to graph y is equal to 5,000. And if I try and look in my original window there, I don't see it because 5,000 is way up there. So I'm going to hit zoom 0 and let the calculator pick a window where both functions exist in there. And I don't really care if I see it or don't see it because this is a calculator making a calculation. They just both have to be on the screen. Second calc 5, I'm going to get over here close to the point of intersection, close-ish to the point of intersection, enter, enter, enter. I'm going to let it say that n is approximately 5.2437343, but I need n to be the next largest whole number above that. So I need this to be My n that I need is going to be capital 6. I need to go out to the 6th power for x at least. So that tells me that as I go ahead and look at these terms here, I have -1 to the, let's write the series down again, -1 to the n, summation n equals 0 to infinity, -1 to the n over 2 to the n plus 1 times 2n plus 1 squared. So this is going to be a positive 2 to the first times one to the second minus 1 over 2 to the third times 3 to the second plus 1 over 2 to the fifth times 5 to the second. And remember, I'm only I'm only worried about the first 6 powers here. So minus 1 over 2 to the seventh times 7 to the second. That's going to be sufficient. Now, how does that incorporate with this here? That this is my I didn't write my powers here, but this is x to the this is my x to the 2n plus 1. So my powers were always odd powers. So these are my x values here, and I only need to get a 6th degree polynomial here, which would be somewhere between 5 and 7. So I had to actually go up to 7 to get this to converge. So that's what's going on here. Why is this n 6? And I only went 4 terms and I didn't go 6 terms. I'm looking at the power here, the x to the n, all the way back here to decide and say this 2n plus 1, this power, needs to be greater than or equal to 6. Well, the first time that happens, since it's an odd power, is going to be on the 7th degree term, and that's going to be this term right here. So let's go ahead and use my calculator to say that this is going to be 1 over 2 minus 1 over 8 times 9 plus 1 over 32 times 25 minus 1 over 2 to the 7th is 128 times 49. And I get that this is approximately, I'm going to go to 4 decimal places, 0.4872. Now, while I'm at it, let me show you what the actual summation of this thing up here is, and let me show you that we're close to it. So I can't really do an infinite series on the calculator, but I can make it give me I can make it give me enough terms to where it's going to squeeze out pretty much all the air. So clear, and then I want summation, math, summation here of x equals 0 to, let's just go out 100 terms and see what this is, right? So this is of -1 to the x divided by, and then parentheses 2 to the x plus 1 times parentheses 2x plus 1 quantity squared, and that is my denominator wrapped in parentheses, and I need to wrap my summation in parentheses. So -1 wrapped, denominator wrapped, summation wrapped, go to delete. I had an extra parenthesis in there. So this is approximately 0.47623708446. I'm only interested in going to the nearest 10th, 100,000th, 10,000th right here. And sure enough, we are within a 10,000th here. We're actually within 37 millionths of the correct answer. So that is really, really, really good approximation by only going out the to the 7th term here. So why are we talking about this? Because this is what you need to do probably with computer programs. They can't really add an infinite number of terms, but you can make the calculator program that you're calculating something to figure out, okay, what is your tolerance that you need to be within for the customer, and they can give you a tolerance, and then the program can figure out, okay, how many what degree polynomial do I need to approximate that? Let me get that polynomial, and then let me go ahead and report an answer back with a finite number of terms that is within the acceptable margin of error for the infinite series. And your program is very efficient this way. So your calculator kind of does this. It has a very small margin of error that's allowed. It may need to calculate a dozen or so terms for some of these transcendental functions to report it within the margin of error, maybe more, maybe less, depending on what your value is that you're trying to calculate. But it's very good at what it does, that it can get these polynomials like this, and that it can just quickly add, subtract, multiply, and divide and give you an answer that's accurate well beyond what it reports out here. It reports usually out to 12 decimal places, I think, in a float. It can give you some more, it can give you some smaller answers or some larger answers with the scientific notation that it writes. But all that being said, it really comes down to that it is using this type of idea of a Taylor or a Maclaurin series to calculate all these things like sine, cosine, tangent, hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic secant, hyperbolic cosecant, hyperbolic cotangent, cosecant, secant, and cotangent. If your calculator has those buttons, it would use it for those. Probably also for arcsine, arccosine, arctangent. It uses those. There's series that it can use for things like binomial expansions and all kinds of fun things that it can do behind the scenes. And it's doing this type of stuff behind the scenes. I'm not absolutely certain what the code is in the calculator because it's proprietary, but I'm guessing that it uses this type of math behind the scenes because polynomials are very simple for the calculator to do. They're very efficient. And if it just gets enough terms, it can report the answer back to any given level of precision that it wants to. And it can do it very quickly. Whereas in infinite series, anything that's an infinite loop that the calculator has to do is going to lock it up, right? It doesn't know when to stop. So it can't do an infinite number of calculations. It has to choose a finite number of calculations that's good enough. All right, so that wraps up our discussion for 9.10. I hope that that is helpful to you to see how we can approximate pretty much any function with centered around a point with a polynomial. And this is an extension of that idea of linearization that we did in Calculus 1, where we said that right around our point of tangency, we can use the tangent line to approximate the function. Well, we got better approximations now where it agrees at the point, it agrees with all of the nth derivatives right around there, and it very closely matches, or now we've gotten something that exactly matches the function that is a polynomial. And we think polynomials are great because we can use the power rule to differentiate and integrate them. And we're going to use this idea when we don't know how to use any other technique in differential equations. We will turn something into a power series solution in the form of y is equal to summation n equals 0 to infinity a n x to the n, like so. And we'll take all the derivatives that we need or the integrals that we need, and we'll come up with a generic solution for our ANs and write a series solution. Sometimes it will be able to be written in this form, compressed down into sigma notation. Sometimes we won't be able to establish a pattern, even though it's there. We won't be able to really be able to express it nicely like this. And we'll write our 1 or our 2 or our 3 solutions for our functions that have this type of a pattern. And that'll be it. This is one of our fallback solutions because we know that every type of function that we know about can be represented now as this power series, hopefully able to be centered at 0 like this. And if it can't be centered at 0 because it's something like ln of x that's undefined at 0, then we just shift it. We center it somewhere else. And we center it at 1 or -1 or something like that. And so we do that, and we even learn how to deal with something that's like ln of x that's not defined at 0, and we want to center it at 0 anyways, just because we want to be mathematicians and learn how to deal with that situation. Even though we can always work around it, we come up with power series solutions that are centered at a discontinuity like that. So anyways, this is all introductory to that you will do later in differential equations. I have some videos on that that I have made. If you want to take a look at those later, that would be great. But we're going to be going into the next chapter, which are parametric and polar equations, which is going to be a very good introduction to if you're taking Calculus 3 next. So this was a good introduction to some stuff that you're going to do in differential equations with higher order derivatives and series solutions and things of that nature, which is one of the classes that you can take after Calculus 2. The next chapter is with a little review of analytic geometry and your conic sections and how to express those now in terms of polar coordinates or parametric representations of those curves is a great lead-in to Calculus 3. So hopefully these two chapters here are very foundational to you for both ordinary differential equations and Calculus 3. So see you for chapter 10, and I hope that this has been a good introduction for you to the higher level mathematics that come after Calculus 2. So see you for the next video.